welcome everybody. So we're really in the home stretch now, only 4 sections left, counting this week's sections, and then we'll be have a little bit more of the conic sections. We'll be looking at the hyperbola, and then we'll get into the last topic, this idea of solving systems of equations, and we'll start out with this week 2 variable, and then we'll look at 3 variable situations, 3 equations for next week. With our hyperbola, this is the last conic section that we will look at. We looked at ellipses and circles before, and throughout the course of the book, especially when we looked at that quadratic stuff, you had seen parabolas before. So technically we have talked about that other conic section. It just wasn't lumped in here at the end with these other ones because parabolas, or I should say the quadratic functions that drive the parabolas, more importantly, are used for a lot of other problem-solving applications in college algebra. With the hyperbola, if you remember back to an ellipse, right where I wanted to, it seems like the board is tired today. So with an ellipse, you had the shape, you had a couple of foci, and the distance all around this ellipse, if you were to take the distance from one foci to a point on the ellipse and the distance from the other foci to that same point, D1 and D2 added together would be the same. Even down here, we've got another point. Well, our distances added together from the foci to that point would be the same. And in fact, the sum that we get out of these two would be the exact same sum as we got out of those two. So all around, the idea of maintaining that same distance with those sums of the 2 foci distances, always going to be the same. In an ellipse, or I should say in a hyperbola, it's a little different. This board is being a little crazy there. So with a hyperbola, what we're going to see is a couple of opposing, don't quite call them parabolas, they kind of look like it. So if you're talking about this just, like we are right now, just kind of introducing it, you could kind of think of it like a couple of parabolas facing away from each other. There's definitely more to it, and the equations look totally different, but just give you a sense visually of what this looks like. Your hyperbola is going to look like a couple of parabolas facing away from each other. And we will also have inside these hyperbolas these 2 locations that will become the foci. Or more importantly, let me back that up there. Each one of these is a focus. We'll be drawing all that other stuff on here, so I don't want to get too crazy with all lines pointing back and forth. So we have our foci located inside the cups, so to speak, the cup shapes. And then if I were to draw to a point on the hyperbola from each of the foci, what we would see here, if I did D2 and D1 for this, we would see that D2 minus D1, and they usually throw absolute values around this because they're not always sure what order the subtraction is being done, and they want to maintain a positive result when it's all said and done. But this distance here that we will have found would be the same distance to every single point on the hyperbola. So again, if I put a point over here and were to draw from the focus to it from each of the foci. Label those D2, D1. Well, the difference in the distances there will be the same as distance in the differences to the other point. And you can do this all over the place. And you put another one, let's say even right here. And go over to it from here, go over to it from here. D2, D1. This is going to equal all the other differences in distances from those foci to points on the hyperbola. And this geometrically is how they would describe a hyperbola. You have a couple of focus, the points on the hyperbola are going to be such so that the distances between the focus and any point on the hyperbola, when you take their difference, will be the same. And that is definitely different than up here with the ellipse, because the ellipse was that when you added these two distances together, you ended up with the same thing. So ellipse, you saw a plus sign in the formula. There's a plus sign with these distances. In a hyperbola, you see the difference, a subtraction in these distances. And in fact, it kind of works out kind of nice because with the hyperbola, the formula that we'll eventually see also has a minus sign in it. Okay. So why would we use hyperbola? You know, where do these come into play in real life? You know, before we get too deep into the terminology and too deep into them, I just want to give you a couple of places where they can be really useful. So real life applications of the hyperbola. Comets sometimes will take a hyperbolic path as they pass through a solar system. If you take a couple of rocks and throw them into a pond, and imagine that those rocks are the foci, and then I'm going to use a little circle drawer here and see if I can do this. I'm going to try to do as close as possible, same size there. Then we'll do another one. And one. So these are, you know, imagine these are the ripples coming out from the rock after you've thrown it in, and keep going out like so. And I'm going to have to do a few more of these to make this work, but it's pretty cool when we finally get there. And of course, this is not perfect, but it's getting closer. All right, I'm almost there. More. Try not to get too lost in what I'm doing here. Okay, we're almost there. All these ripples just intersecting with each other. It looks like maybe a kind of a mess. But I'm going to stop right there because I have enough where I can kind of show what's happening. If you were to start at this foci and draw through the intersections of those circles, let's see if I can draw through those, from the two different ripples, this shape that I've created here actually ends up being a hyperbola. And if I would have done these circles all evenly spaced and perfect, which I definitely did not do, you would see a much better hyperbola come out of this. But the idea is that there's a hyperbolic shape that comes out of this. Now, another benefit of this picture, and more importantly, the results of it, is that when you have radio waves, let's say our two foci were radio towers, radio waves emanate out in a similar pattern where there's kind of circular patterns going out, and they can actually pinpoint the location of a ship using the distance, or the time, I should say, that a radio wave takes to travel to a ship from one tower versus from the other tower. And if they do this with just two sets of towers, they can figure out the curve, the hyperbola that the ship is on based on the differences in the times, going back to that relationship between the focus and the difference between the distances giving you the curve. And if they put a third radio tower into the mix, they could create two different hyperbolas, and they could find the intersection of the hyperbolas and then find the location of the ship. So even though that may have been said very fast and kind of went over the head, it is definitely something that gets used in pinpointing ship locations when they have radio towers that can transmit to them. And if you want to look more into that, it's all over the place on the internet. You know, so just go ahead and search using hyperbola to find a ship location with radio waves, and I'm sure there'll be a much better description and, you know, maybe even a video or so that you can watch on that. But anyway, that's one cool place that gets used. Mirrors and telescopes. In fact, the Hubble telescope uses a hyperbolic based mirror system versus a spherical or a parabolic mirror. And all the best telescopes that you can buy typically are going to have hyperbolic, because the hyperbolic does not have the same problems that spherical does. Spherical doesn't always focus the light in on the same point, so some things may look more in focus than others in your field of view. Parabolic, things that are not in the center of the field of view can be made to look elongated, so around the periphery, the stuff might look a little bit more elongated. And a hyperbolic doesn't have any of those two problems. It doesn't have the problem of focus, and it doesn't have the problem of elongated objects if it's not in the center of view. So that's why, you know, a lot of the high-end telescopes that you're going to see out there use hyperbolic-based mirrors. So there's a lot of places in real life where these hyperbolas show up, and not just in cutting through a couple of cones with a plane. That's, you know, the first place where you would see it in this conic section development. But there's lots of different places where hyperbolas come in, and I think overall it's pretty cool that, you know, this shape that you're going to be working with can be used for so much stuff. Okay, so let's get into some terminology now and start looking a little bit more along the lines of what you're going to be using these for. You will have a couple of word problems to deal with where, you know, I want you to get your head wrapped around a little bit more in a problem-solving sense. But overall, you know, most of what we're going to be doing here is going to be illustrated in this video today. So terminology. I'm going to go ahead and pull in a couple of boxes to talk about this, because I feel like they do a pretty good job with pictures compared to my picture ability. And let me get this thing up here so I can copy this. So just like with ellipses, the hyperbola also can be turned in one of two ways. You're either going to see the cups or the, you know, parabola-like objects opening up left and right, as we see here, or we're going to see them opening up and down, and we'll see that here shortly. A couple of things terminology-wise I want to make sure that you have. These dots here and here, and let me use a different color just because here, we got green in there, but these two dots here, those are your vertices. So there's two vertices in a hyperbola, just like with an ellipse. In between the two vertices, they have what is called a transverse axis. It transverses between them, if that's, you know, even the proper use of English there. But vertices are between, or are at the ends of, I should say, the transverse axis, which I've drawn there in blue. So vertices at the end of the transverse axis, and then you have an axis that will go through the center, but meeting perpendicular to that transverse axis. And they call this the conjugate axis. So you have the conjugate axis that splits a hyperbola into two equal mirrored halves. And then we have our foci in green. So our green dots here, those are each the foci. And I won't draw the arrow over to the other one because it makes that picture a mess. But just know that it is in green and it's the other dot. And then we have our center in black. So the center right here. And let's see, I think that's all the main ones, but let's make sure there's nothing too crazy here. Okay, that's all the main terminology I wanted to get out there. You have your vertices, your center, your foci, the conjugate axis, which splits it, and then the transverse axis. And they like to use all this terminology throughout the problem, so that's why I'm making sure to get it in here. A couple other things over here on the left to be aware of. How do you get from this formula down into some of these other pieces of information, you know, your location of the foci, location of vertices, etc. Well, before we get there, just notice with a horizontal transverse axis, so the blue line that I drew in being parallel to the x-axis, horizontal, the y term is negative. We have that minus the y minus k quantity squared over the b squared. So we're going to see with the other one that the x will be negative, and then that's what's going to make the cups go up and down, basically. So just be aware of that. That is an important feature as we get into these and you're sketching them. It's real important to know where your transverse axis is. So if x is positive, then you're going to have a parallel transverse axis. And when we see x is negative, you'll have a vertical transverse axis, and we'll get there shortly. Some other things to take away from this. From the center, notice that if you go a units to the right, changing the x value here by a units, and you go a units to the left, so subtracting away a units, or the square root again of what is underneath the x. Still nice here, just like with the ellipse, whatever was under that x, you take the square root of it, tells you how far to go left and right. Similar thing with hyperbola. We take that square root of whatever is underneath that x term, and we can go left and right from center and find those vertices. Whatever is underneath the y, well, we still can go up and down from center there, and you might be asking yourself, well, that's not anywhere on the hyperbola, so what good is that? Well, the good is, if you look at this picture real carefully, you see this kind of box here that I'm just kind of putting a couple of dots around the corners. That dotted line box that they have there, that dotted line box, I'll probably call it the guide box. You know, the book may call it something different, other books call it other things, but I'll call it a guide box. And really it is a guide to help you draw a hyperbola. And without the b being added and subtracted from, in this case, the y value of the vertex, we wouldn't be able to get the full shape of the guide box, because once you get that guide box in play and connect the diagonals through with those other dotted lines going through at the angle through the center, those angled lines are asymptotes to the hyperbola. So the hyperbola is going to grow close to those but never cross them. And then the left and right, in this case of the guide box, are the places where the hyperbola actually touches at those vertices. So even though we don't see the value, the square root of the value underneath that negative term showing up explicitly on the hyperbola curve, it is very important to help us sketching a hyperbola. Very important for that. Okay. And let's see then some other things. So define the foci. In foci, ellipses, if you had a and b, or a squared and b squared from underneath your terms in standard form, you would add them together, a squared plus b squared, and that would help you get c squared, or the, once you took the square root, the distance from the center out to the foci. Well, in a hyperbola, they have this, I'm sorry, it was b squared minus a squared in ellipses. I'm looking at this formula and going crazy here. So b squared minus a squared in ellipses. Sorry about that, misspoke. In a hyperbola, they write this form like this in this book, and that's kind of what threw my mind out of whack there for a second. It is a squared plus b squared equals c squared. So the sign in the formula is opposite what you need to do with the a squared and b squared in order to find the c squared. In an ellipse, it was plus in the formula, minus in between the b squared and the a squared. And a hyperbola, it's a minus in the standard formula, and it's a plus in between the a squared and the b squared to get the c squared. They just write it kind of weird in this book, and I don't understand why they do that. And sorry about that for misspeaking there. But you can always just do a squared plus b squared to help you get that c squared. And then the asymptotes, they actually have these equations for the asymptotes. And notice that in this particular form, what we have is from the center, we would go up b units, and then we would go over a units to get to this point right here that I'm making really big and red right now. We would need to get, or rise b and run a to get over there. And that's where we see this little slope, b over a coming in. And then otherwise, it's just a point slope form. The asymptote passes through the center. So we have hk being the point. The b over the a becomes the slope. And you plug it in that point slope equation of the line, which, if you remember, was that y minus y1 equals m times the quantity x minus x1. Now, where does the plus minus come in? Well, there's two asymptotes. There's one where you rise b and then run a to get over there, the one I first drew. But there's also another asymptote where you would actually rise negative b, or drop down b units, and then run a to get to the next point from the center. So because of those two different asymptotes, we have the plus or minus in play. One for the positive slope asymptote and one for the negative slope asymptote. Okay, so that's horizontal transverse axis. Cups open up, left and right. Next one we'll look at, slightly different. It's just going to be something that's been rotated, but still pretty similar. Terminology-wise, it's still the same basic terminology, but just make sure we're all on the same page with where things are now. So in a vertical transverse axis, we would have the two vertices connected like so with that blue line. That would be the vertical transverse axis. It always transverses between the two vertices. Our foci are now up and down, so we have to change the y value by adding or subtracting c to it in the vertex. To get up to our vertice and down to our other vertice from the center, which is still this black dot here in the center, we're taking the h and then k plus a and then k minus a. It's like, wait a second, I thought a was attached to the x. And this is another place where it really kind of annoys me that they even put these letters in here, because if you look at the standard form, just like they did with the ellipses, they changed that location of the a and the b, depending on which was positive, which was negative, in terms of signs here. You can also ignore this for the most part if you remember this one key thing again, just like with ellipses. Whatever is underneath the x, I don't care what they call it, a or b, whatever is underneath the x, whatever number ends up underneath there in the standard form, you take the square root of that, and that's how far you go left and right to get to, in this case, the endpoints that will determine the boundaries of your guide box. Underneath the y, whatever is underneath there, take the square root of that and go up and down that many units, in this case, to get to the two vertices. So don't get caught up too much in the a's and the b's and worrying about their placement. Just know that however far you're going to go left and right, you square that, put it under the x. However far you're going to go up or down, square that, put it under the y. It works with ellipses, it works with hyperbola as well. Okay, all the other basic pieces of information, in this case, our conjugate axis is now running horizontal where that black line segment is, or there's two black line segments there. Still have the foci in play. We've got our vertices in play. A lot of the same terminology there. And again, I don't know why they write this way. It's so hard to get a pattern between the two, comparing ellipses and hyperbola. But you can add the a squared and the b squared and get c squared, which will help you get to the distance that you have to go from the center to get to your foci. And again, in this one, the only difference between our asymptote formulas is that because they switch these letters around, which I will agree is kind of annoying, the rise is determined by the A, the run is determined by the B. Now, in practice, again, as long as you put what is underneath the y, the square root of that, in the numerator of your slope, and whatever is underneath the x, the square root of that, is the denominator in your slope for these asymptote equations, you're going to be fine. It'll work every time. Don't worry too much about a's and b's. I never do. I just know that left and right is going underneath the x, up and down is going underneath the y, and hyperbola for the asymptotes, whatever's under the y helps me get to the numerator of the slope. Whatever's underneath the x helps me get to the denominator of the slope. It's still rise over run or y's over x's in that slope. Okay, let's go ahead and see some examples in getting into some problems more along the lines of what you will be doing in homework and give you a sense of how to do this stuff. So number 5, I'm just going to copy this one in again. I feel like it makes it a little easier. As soon as I get to the problem set. Okay. So in these exercises, we're going to determine the center, the transverse axis, and here I'm pretty sure all they want is horizontal or vertical. I don't think they want an actual equation from this, from what I was looking at earlier. And they want the vertices, the foci, and the equations of the asymptotes, and then sketch the hyperbola. So we're going to do all of this stuff. And I'm going to do this for problem number 5. Now, the first thing that you have to do with any of this, and this is the reason I'm picking this one because it's a little bit more along the lines of what you might see on the exam, you got to get into standard form. And hyperbola, just like an ellipse, standard form means you're equal to 1 on one side, and then you have fractions on the other side. So here I'm going to divide everything by 100, every term by 100. And this will get me x squared over 5 minus y squared over 20 equals 1. And now as soon as I see this, I can go to the center, looking for the HK. H is still always attached to the x. K is always going to be attached to a Y. Here I don't see anything attached to either one, so the center is just going to be 0, 0. The transverse axis. Since x is positive, since the x term is positive here, x is dominating this thing, so to speak. One way to think about it, x-axis is horizontal, the transverse axis will be horizontal. Which means we're going to be looking at a basic shape like that for our hyperbola. And again, the transverse axis connecting the vertices through the center. You put all that together, it almost looks like an H. That would say horizontal transverse axis. Maybe not, but if it helps you remember it, use it. Okay, vertices. You define these. Now the vertices in this case on my little basic sketch are located at these two locations. I know the center is 0, 0. I also know that the left-right distance to each of those is the square root of whatever is underneath the x. So here we would have A just equaling square root of 5. And since I'm going left and right from the center to get to those, I'm going to adjust the x value. So I have 0 plus or minus the root 5, comma 0 being the simple form of the vertices, which would give me root 5 and 0 or negative root 5 and 0. That's our vertices, and now we need the foci. So for our foci, I need to know the value of C. And once I get the value of C, I'll be able to add and subtract that from my x value of the center in order to get left and right out to the foci. So we have here that C squared will equal the A squared, or 5, plus B squared, or 20, which equals 25, which is very nice, because that means then that C equals 5. And if C equals 5, then I can get the foci as being 0 plus or minus 5, comma 0. Take that x value, add and subtract the C value to get out to the foci with these horizontal transverse axis type problems. So we'll have 5, 0 or negative 5, 0 will be a location of our foci. So we have our vertices, we have our foci. Last thing we're going to need here, the equations of the asymptotes, and then we'll sketch this hyperbola. The equations of the asymptotes. For this one, we have the form y minus h equals plus or minus the b over a in these, and then x minus k in parentheses. So just plug in what we know about the different values. Remember that even if you forget about the a and the b, whatever's underneath the y goes in the numerator once you take the square root of that. Whatever's underneath the x after you take the square root of that goes into the denominator for the slope of your asymptote. So I have y minus 0 equals plus or minus the square root of 20. That was what was under the y, was 20, so that takes square root. And then over the square root of 5, and then times quantity x minus 0. Now for those who love to simplify, good, because you should do that here. Remember that if you have the same root in numerator and denominator, you can put the whole thing under that common root. And 20 divided by 5 is 4, so the square root of 4, which actually ends up equaling 2. So now we'll have y equals plus or minus 2x. Getting rid of the minus 0, because that really doesn't help us much. And that becomes the equations of our asymptotes. Y equals positive 2x and y equals negative 2x. got to sketch this. And this is where that guide box is going to be crucial that I mentioned earlier. To sketch this thing, the first piece is put in the center. So we'll have the center there. We'll call this X and Y axis. So I'll put center in at 0, 0. And now I'm going to go left and right, the square root of what was underneath the X in the original standard form. Standard form had square root of, or 5, I should say, which would give us square root of 5, which is a little bigger than 2. So we'll go out 2, and again, I'm getting that from square root of 4 equals exactly 2, square root of 5 should be a little bigger. So I know I'm going to have a little dot here and a little dot here. And in fact, those 2 dots I just drew will be the vertices of my hyperbola. Right. For the y, looking underneath the y squared term in the standard form, we saw 20. Square root of 20 is going to be in between the square root of 16 and the square root of 25, the 2 perfect squares that I actually know there. The square root of 16 is 4, square root of 25 is 5, so square root of 20 should be between 4 and 5. So I'm going to go ahead and put that many tick marks up here, and I'll put a little dot somewhere in between 4 and 5. We'll go ahead and call that right in there. If you want to get super precise with the calculator, highly recommend go ahead and do that, but for the purposes of a sketch, ballpark is going to be just fine. Okay, now that I have those 4 dots drawn in, I'm doing those new 4 dots around the center, I'm going to use those to help me define a guide box. And this should be drawn dotted. It is not part of the hyperbola. It is simply a tool to help you sketch a more accurate hyperbola. So draw your guide box. And then we're going to draw in our asymptotes by drawing diagonals through the guide box. And again, those should be dotted. They're not part of the hyperbola. They're just here to help you draw it. And you may want to go out a little further and give yourself a bigger picture or whatnot. And the last piece was kind of terrible. So there you go. So now you have the guide box in. You use it to draw those asymptotes as I did. And just as a quick check here, I'm curious how close our sketch is to what we should be seeing. Notice that if I do go from the origin up to and over 1, I do get pretty nice placement for what I should be seeing based on the equation for the asymptotes. Y equals 2x means that I should have a slope of 2 from the origin. I can go up 2 and over 1 and get to another place in that asymptote. So my sketch is actually not as terrible as I thought it might be. Last but not least, I've got all this guide stuff in here. Well, let's actually draw the hyperbola. So the vertex will be, in this case, left and right of center because of that horizontal transverse axis. And then you're going to draw in some cups or parabola-like objects that look like they're getting closer and closer to those angled asymptotes that you drew in. And then they should touch and connect at those 2 points that you drew left and right, in this case, of center. And that, to me, would be a perfect sketch if I were to ask you to do something like that on the final, which is highly possible. Let's take a look at another example. Let me just grab what they want us to do here. Now this one, they give us a little bit different information than what they gave us in the first one. The first one, they gave us almost exactly what we needed to start the ball rolling. Here, though, all they want us to do is determine the standard equation of the hyperbola with given excuse me, given characteristics, and then sketch the graph. So here they tell me the center is at -6, -1, a focus is at -6, -9, and a vertex is at -6, -5. So let's just do a quick, very rough sketch of these points, just so we get a sense. Is this a horizontal transverse axis or is it a vertical transverse axis? And the center, -6, -1, and we'll call that somewhere about in here. And then -6, -9 would be a focus, so we'll call that down here. And then a vertex, -6, -5, we'll call that about in here. So for all of these, from the center, I had to go straight down to get to a vertex. I had to go straight down to get to a focus. And more importantly, I had to go straight down to get to the vertex, which means I would go up to get to the other vertex. I go up to get to the other focus. And the vertex then, being up and down from center, would drive a horizontal transverse axis, or a vertical, I'm sorry. It's like saying the word horizontal two different. So, okay. Vertical transverse axis. And that's just coming from doing a quick sketch and the information that we should know about how vertices, foci, and centers are related to each other in hyperbola. Okay, from there then, what other things can I get? Well, if I know it's a vertical transverse axis, I need to, get a basic form in here. And what we're going to have is y minus k squared over the a squared minus, I'm sorry, y minus h still. Sorry about that. No, it is y minus h. I'm going to chalk that up to Monday. So then we have x minus h squared being the minus, or negative term, and that'll be over the b squared there. And then this will equal 1. So our goal here, once you figure out it's a vertical transverse axis, I highly recommend you go ahead and write down that formula. Write it down right away. And then it becomes real clear what it is you're looking for. We're looking for an HK. I need my center. I need a value for A. How far do I go up and down from the center, and then I'll square that to get to a squared. And I need a value of b. How far do I go left and right from center? And then I can square that, excuse me, to get my b squared. Well, a lot of this information was given. We have the HK. Given is the center, -6, -1. All right away, done. The vertex at -6, -5. Well, that tells me that from this y value of -1 down to this y value of -5, if I were to find the difference in those 2 points, it's a difference of 4. So I know already that A, the difference between these, if we do -1 minus a -5, we're going to end up with -1 plus 5, or 4. And this is going to equal A. It's how far I had to go up and down. It's what's underneath the y squared term. So I already have that. I got that in play. That's great. Find B. It's like, well, they didn't give me anything about the left and right from center. They gave me nothing about that, in fact. But they did give me a focus. And if I have A and I have a focus, I can use that relationship in hyperbolas that a squared plus b squared has to equal c squared in order to get the b out of that. So let's go ahead and figure out how far away the focus was from the center, and that'll give me my c. So down here at -9. Well, -1 to -9 is going to be 8 units. So c is equal to 8. So I got c is 8, a is 4. And I can go ahead and square those. So I'll have c squared equals a squared plus b squared. Or 64 equals 16 plus b squared. 64 minus 16 is going to be 48. And that'll equal b squared, which I don't need to go down to b until I sketch it. But right now I can just leave it as it is. I got b squared, that's what I need for the formula. So I can go ahead and create the equation in standard form by just plugging in the center, this a value that I found from the given information, and then this b squared value that I found by using the known relationship between a, b, and c in a hyperbola. So we'll have y minus a negative 1. It's always going to be y minus whatever is the y component of the center. And the two negatives will make a positive, so we'll have y plus 1 squared over a squared, or 16. We'll take 4 times 4. We'll have minus the x plus 6 minus a negative 6 to get there. And then square that quantity and put that over the 48. And then this will equal 1. So that right there is one part of the answer. Just want the standard form of the equation for this hyperbola. And then they want us to sketch it. So for the sketch, come down, start your graph. We're going to go the negative 1 down. I already know that. I'm going to go negative 6. So 6 to the left. So negative 6 and negative 1, I'll have my center. And then I'm going to go up and down from that 4 units. So from negative 1, I'll go to positive 3, and from negative 1, I'll go down to a negative 5. And again, that's coming from the square root of what was underneath the y. And my tick marks are a little bit more spread out, so this is going to look a little funky. Will be a little out of scale, but we'll live. And then the left and right is the square root of what's underneath the x. So square root of 48. I can take 48 divided by 16 and get 3. And this is going to end up being 4 times root 3 out of there. Another way to think of this, 4 root 3 is still kind of hard to picture how far that really is. But if you think of the square root of 48 as being really close to the square root of 49, which is 7, we could think, okay, well, I just need to go just a little short of 7 to the left, a little short of 7 to the right for these inputs in my guide box. So I'll go 1, 2, 3, 4, 5, 6, a little short of 7 here, so I'll do right there. And 1, 2, 3, 4, 5, 6, a little short of 7 there, so I'll have this one there. And then we'll start creating my guide box and asymptotes. Asymptotes through there. This box is definitely not as good as I've drawn on other problems, but all the basic information is there. And now we have to keep in mind, once you get this guide box drawn in, it's not really clear where your hyperbola cups go. So we do have to remember that our transverse axis was vertical, which means our vertices were above and below the center, which means that our cups will be facing up and down. Okay. All right, so that's number 10 there. Let's take a look at one more for this. Again, I need to copy this from over here first. We're going to take a look at number 18. Just want to give you an example of what happens when your center is not at a nice place. Okay, so in this problem, it's a little bit different than what they've asked in the other one, especially at number 5. They want you to find the center, vertices, foci, that's just all the same. But then the endpoints of the conjugate axis, not the transverse axis. Got to be careful with the wording there. And the equations of the asymptotes of the hyperbola, and then sketch the graph. Well, all of this information is going to hinge on standard form. I can get the center straight out of it. I can get to the vertices and foci and endpoints of the conjugate axis and the equations of the asymptotes when I get that information out of the standard form. And then, of course, I'll be able to sketch that graph as well. Standard form, looking at how this equation is written right now, not even close. Excuse me. So I'm going to start putting my x's together. And the reason I'm doing this is because I can see immediately, and you should start getting used to this, I am going to need to do some completing the square in order to make those parentheses with the x minus h, y minus k quantity squared. So I want to get my x's together, the y's together. And then furthermore, what I'm going to do is get this set up for adding some stuff in for completing the square. So I'm going to form some parentheses. With the 16, the negative 16 in front of the y squared, I definitely need to factor that out of all the y terms. So I'll have y squared and then minus 4y. 16 will go into 64 4 times. And when I distribute negative back into that negative, I'll get positive 64y back. And oops, now I want to make sure I leave that blank for adding something in to complete the square. Now on the right side, I moved that 55 over and it became positive when I did that. And now I'm going to add in whatever I'm going to add in for the x. And then I'm going to have to go minus 16 times whatever I add in for the y. Again, with these completing the squares, when you're solving for the standard form, you've got to keep in mind that if you factor anything out of that y squared and that other y term and put it in front of the parentheses, when you complete the square, this number that's going to go right here is technically being multiplied by negative 16 too, because it's inside that parentheses, which means it's technically changing the right side or the left side of the equation by negative 16 times that amount, and we better do the right side by that same amount if we're going to keep this equation balanced. So I always kind of set up this basic template so that I don't lose sight of that when I'm moving forward. Now with the 10 in front of the x, we'll take half of that. We did 5. We will square that, and that will give us 25. So that's what we add in here to complete the square, and that's what I'm going to add in on the right side to keep this equation balanced. For the y squared, we'll take half of the 4 and we'll square it. We'll take out 4 to get 2, and we'll square it and get 4. I'm not going to worry too much about the sign here when you square it. It's just going to go positive anyway, and this sign right there is going to go down into the parentheses anyway. So I don't need to worry too much about that. But what I do need to worry about is putting 4 over here. Now, some of you may have looked at this and said, oh, with that negative y squared, I can immediately go to that transverse axis that was horizontal, or a vertical conjugate axis. We got to think about that in this problem. However, in these problems, and you want to be careful with this, there is the possibility that when you complete the square, this right side ends up being negative. It's very possible that that could happen. And that means you'll divide every term by a negative in order to get to that positive 1. And that will change the nature of the axes based on what you may have thought originally versus the true value. So be careful with that in these problems. Sometimes you'll end up with a negative on this right side, and you will have to divide by a negative, which will change the sign on the x's and the y terms to different than what they started with. Something to be aware of. Okay, moving forward in this problem, I can go ahead and write this as x plus 5 squared, taking the plus sign again from in front of the single powered x term, minus 16 times the quantity y minus 2 squared. Again, taking the sign from right there, and 2 from half the middle term. And then this will equal, well, 55 and 25 is going to be 80. And then 16 times 4 is 64. So 80 minus 64, because that second piece there is going to be negative. It's technically the third piece. 80 minus 64 will be 16. So we'll get 16 here. And now I need to divide everything by 16 in order to get a 1 on that right side and get me into my standard form. So now we'll have x plus 5 squared over 16 minus y minus 2 quantity squared. I'm going to force this to be over 1 just to have that in play, and then this will equal 1. Okay, so that's the standard form. I know it may seem like a lot of work to get there, but that work's going to pay off because now I can get all this other information very easily from the standard form. So the center, we're going to have h from the x piece, so that'll be a negative 5. There's plus 5 in there, which means I got to make it a negative 5 or minus a negative 5 inside to get my h. And then k will just be 2, so negative 5, 2. My vertices, or let's see, I want to close that first. So for the vertices, well, it is helpful in this one to get an idea of how this thing is facing. Seeing the negative y, we will have a horizontal transverse axis, which means we'll have our cups going left and right, which means that my vertices will be left and right of center, which means I need to take what's underneath the x squared term, find the square root of that. So we get a equals 4. And then that's what I'm going to add and subtract to the x value of the center to get to the vertices. So we'll get negative 5 minus 4, or negative 9, comma 2, or negative 5 plus 4, which would be a negative 1, comma 2. So that'll be our two vertices. The foci, well, I have 16 and 1 is my a squared and b squared. So I can go ahead and find c squared by doing 16 plus 1, or c squared will equal 17, which means that c equals the plus or minus square root of 17, or technically we just need the root of 17 because we're going to add it and subtract it anyway. The foci are also, in this case, located left and right from center. So we'll have negative 5 plus or minus the square root of 17, comma 2, which will take us to negative 5 plus root of 17, comma 2, or negative 5 minus root of 17, comma 2. So those are our two foci. And let's see what else. Endpoints of the conjugate axis. Now this one, got to be careful here. Let's go back to our little tiny sketch. Here, the conjugate axis runs perpendicular to the transverse axis, and the endpoints here on this conjugate axis are units up and down from center. which means that I'm going to take the square root of what was under the y to get b, and square root of 1 is just 1, and then I'm going to add that and subtract that from not the x value anymore, but the y value of the center, because I need to go up and down now, change the y value. Now we'll get -5, 3, or -5, 1. Those will be the endpoints of our conjugate axis. And then last but not least, equations of the asymptotes, and then we'll sketch it. Equations of the asymptotes, basic form is y minus k equals plus or minus. In this case, it will still be b over a, and then quantity x minus h. So we'll have y minus 2 equals plus or minus 1 over 4 times x plus 5 in the quantity. And if you forget BA stuff, just remember the numerator, the slope is the rise, so it goes with the y's. Square root of what's underneath the y term, we got 1. The denominator is the run, it goes with the x, so it's the square root of what's underneath that x, and that's what we got before. So you could simplify that, solve for y. They may ask you to do that on the online homework, and you'll get 2 separate equations, but on an exam, I would accept this. Last but not least, now we sketch. And for this sketch, we need to go -5 for x. Make sure I give myself some room to do some other stuff. Right there, and then we'll go. And for y, we need to go 2. And there. So then our center at -5, 2. That going in. We'll go left and right from center 4 units. So 1, 2, 3, 4 to -9. 1, 2, 3, 4 back to -1. And we should see that verified up in our vertices, because those are going to be the vertices. -9, 2 and -1, 2. So that checks out. Then for our up and down from center to finish our guide box key points, we'll go up 1 unit from the center and down 1 unit from the center. And if we check those, we should be seeing -5, 3 and the -5, 1, and we are as the endpoints of our conjugate axis. And then we'll draw a dotted box through those, draw your dotted asymptotes through the diagonals of the box. And now, since this was a positive x, the transverse x or axis is horizontal, which means that we're going to have our cups of the hyperbola and something like this. Opening left and right. And that's all I need to see. So as long as you have that stuff in play, I'm going to be good with your answers. And that takes us to the end of what we're going to be looking at today for hyperbolas. Moving into something completely different, we'll look at 11.1, and this is systems of linear equations. In 2 variables. Now, what does this mean? You know, systems of linear equations in 2 variables, and that could just be Greek to a lot of you. And first thing we should take away from this is what it means to be a linear equation. So a linear equation, all the powers of the variables are going to be 1. And since we're going to be doing a lot of x and y here, you can think of it as all the powers for x's and y's will be 1. That's the linear piece. A system. So we're going to have a system of linear equations. Well, a system in this context of mathematics just means that there's going to be more than one equation and the goal is to find a solution in 2 variables, so a solution x comma y, that satisfies all the equations in the system. Now, for most of what we're going to be doing, it's just going to be 2 equations. So you'll have 2 equations with 2 variables each, and we want to find a common x, y that makes both the equations in the system true. That's the goal here. So for example, maybe our system is x plus y equals 3 and x minus y equals 1. A point that would satisfy this would be 2 comma 1. If I take 2 plus 1, I get 3. If I do 2 minus 1, I get 1. So this point here, 2, 1, will be the solution for the system. That's all they mean by that long, lengthy title. System is just more than one equation. Linear equations means that all of your variables are going to have single powers or powers of 1. And then in 2 variables means that you're only going to see 2 true variables in that system. In this case, in the example, it was x and y. It could be s and t, it could be u and b, it could be a lot of different things in practice. But for the most part in this book, they stick to x and y. Will you potentially see systems of nonlinear equations? If you move into pre-calculus, there is a chance of that. Could you see systems of more than 2 variables? Stick around for the last couple of sections of this class, and yes, you will see that. So all these words in this title are important because you could see things that are nonlinear and have more than 2 variables. So it is, you can't just say solve a system in math and know what you're talking about. You have to put in those other qualifiers or quantifiers. And because our focus right now is going to be on 2 variables, I do want you to understand that, you know, we could really graph the solution of these. And more important, because I'm looking at this x plus y, x minus y in that example, or in general, it's going to be y with a single power, x with a single power. I also know that when it's a linear system, they're always going to be straight lines. So if I come down here, I'm going to draw 3 different things because there's 3 different possibilities that we'll look at. And if I have my little XY grids ready to go, we could have the situation where, much like in the example, our two lines, and this is not what they are, but x plus y equals 3, x minus y equals 1. We could look at those, and if these lines were representing that, we would have found the one solution right there where those lines cross. So visually, these systems can be done. And if you're kind of getting stumped on this, don't be afraid to put these into a little graphing applet, something like Desmos, which is a very easy to use graphing application on the computer, free as well. So desmos.com, DESMOS. If you have a graphing calculator, you can put in these lines and you can see where they cross and get an idea of what the answer is. Now, it is possible that you may have lines that are parallel. So those parallel lines, well, they're never going to cross. Parallel lines don't cross. It's the definition of parallel lines. So this would be no solution. So we have the possibility of one solution over here. We could have no solution. We'll see how this works out when we start doing some of the example problems. I want to do these here shortly for you. And the last possibility, and you got to make sure that you're really watching this closely right now. If you've got your eye on something else, make sure you're watching this because this is going to be a little crazy. All right, so I got one line there, and then I got another line right on top of it. And that case would be called the infinite solutions. You may be saying to yourself, how the heck's that going to look in a problem? If they gave me the same line twice, don't you think I would know that it was the same line? And sometimes they disguise it. So they might give you something like x plus y equals 3, and then 3x plus 3y equals 9 as your system. And then when you start really looking at that, the second equation, if you divide it all by 3, just gives you back the first equation. And right there, it's like, well, they're basically the same line. So all the same points that would satisfy the first equation would also satisfy the second, which means that you will have infinite solutions to that system. And we will have to work with this type for the way they want the answers written. And again, I'll demonstrate that in the examples. Before we get too crazy with solving and actually looking at examples on these, just a couple more terminology that they've attached to each of these conditions. So our terms here, they would call the one solution case consistent. There are solutions that go with it. So the equations in the system are said to be consistent with each other. There's something that will make all of them true. Well, with an infinite solution case, you also have consistent. All the equations there are in an infinite solution case, all the points that work for one work for the others. So the solution is consistent throughout. In a no solution case, they call this inconsistent. Something that works for one of them does not work for the other, so it's inconsistent. In terms of variables and how they relate to each other, what they would say for the one solution case is that it's an independent situation, which means that the x didn't depend on the y to get to your solution, and the y didn't depend on the x to get to the solution. The no solution case, technically these are independent, and their answers are inconsistent, but there's nothing saying that the x and y are depending on each other. Well, in the infinite solution case, there is some dependency. And because they only give you, in this example here, x plus y equals 3, 3x plus y equals 9. Technically, it's the same equation, x plus y equals 3. And any x and y that would solve the other. So that's what makes it consistent. But if I want to find a bunch of x's and y's that make this work, I'm probably going to have to say something like, okay, well, the solution set would be x's that I pick, and then for the y, we would subtract x over, solving this little equation up here, and we would get 3 minus x would give me all the y's. So notice that from this one equation that kind of determines everything in the infinite solution, our solution set, it's infinite. I don't want to have to list them all out. That'd take a long time. But I can write it in such a way where it's like, well, if I know the x, if I pick an x, I can just plug it in and solve for the y that would go with it. And in this case, when you solve for the y that would go with it, you get 3 minus x. So we can write these dependent cases, these infinite solution cases, as x comma 3 minus x. Or even if you really want to get crazy, sometimes they'll say, well, use y as the independent variable. So we'd have here, y is what you get to pick. And then if you solve for x, you get 3 minus y in this case. So either one of these two, depending on how they say to use something as your independent variable. Make sure this is clear here. X is independent in this one because you get to choose it and then use it to find y. And for this one, y is independent because you get to choose it and then use it to find x. And depending on the homework problem, they may ask you to do something a little different than that. So just be aware of that as you're getting into these with your infinite cases. Okay. So how do we solve these? I've talked a lot about the names that are attached to solutions, but how do we actually solve these? And in order to solve these, they give you 2 different methods for these 2 equation, 2 variable systems. And the 2 different methods, I'm going to go ahead and just open this up here real quick. They are called the substitution method and the elimination method. I'm going to pull both these up here, and in the examples, at least the first couple of examples, I'm going to use both methods just so you can see the difference between the 2. Sometimes one method is definitely going to get you there quicker than the other, and in all honesty, the decision between the 2 sometimes does come down to practice or just preference. Maybe one of the methods sticks out to you and it's like, wow, I really like that one. It just makes sense over the other one. And in this class, you may be asked to do both methods. It is, part of the class you're supposed to know how to do both. So I may ask you to do a specific method on an exam. So just be aware of that moving into the final. I don't want to blindside you with that. So just be aware that you should practice both of these in order to prepare yourself well for the final. But after you get out of this class and in general, it really is something where, pick the one that you like to use the most. They should both get you to the same answer. With substitution, you choose an equation and solve for one variable in terms of the other variable. And you substitute the expression from step 1 into the other equation. And then you solve the equation in one variable. And then you substitute that value found in step 3 into one of the original equations to find the value of the other variable. Now we'll illustrate this as we go through problems so that you can see that. With the method of elimination, you choose a variable to eliminate. Then you multiply one or both equations by an appropriate non-zero constant so that the sum of the coefficients of one of the variables is 0. And if the variable is 0 or the coefficient of that variable is 0, that means that essentially it goes away and you've eliminated it. Then you add the two equations together to obtain an equation in one variable. And this little piece here is just using the fact that if you have 7 equals 2, or 7 equals 7, crazy, I'm going to do 2 equals 2, not like that. So if you have 7 equals 7 and 2 equals 2, if you add the left side, you get 9. If you add the right side, you get 9. And you maintain equality. And that principle will always hold. If you have things that are equal, you add the lefts together, you add the rights together, the equality is maintained in your result. So when you add the two equations together to obtain an equation in one variable, that one equation in one variable is what can be used then to solve the equation in one variable to get an answer for one of the variables. Then you substitute the value obtained in step 4 in one of the original equations to solve for the other variable. Last step is pretty much the same in each of these. Let's see some examples, because I feel like just reading through that probably did not make it clear as sunshine. I'm more clear like mud. Somewhere in here is a problem set. Here we go. Okay, so let's take a look. Now, even though they'll tell you a certain method, I'm going to kind of go away from this one. So I'm going to jump to both methods, just so, again, so that you see this. So we're going to solve this system. Okay, first approach I'm going to use is substitution. So what you want to look for when you're doing substitution is, out of these two equations, which one is going to be easiest to solve for one of the variables. Now I see a single x in this top equation, I see a single y in the second equation. However, the second equation has a negative y, which means I have to deal with that. So it's technically not a pure 1 coefficient. The top equation, though, if I just subtract 4y from each side, I'll get x alone right away. So that, if you can, that's the thing you want to look for in substitution. Find something that you can solve for easy in one of the two equations. So here we'll have x equals 5 minus 4y. Coming from there. Now, and that's choose an equation and solve for one variable in terms of the other. So that's step 1. That step there. In step 2, we're going to substitute the expression from step 1 into the other equation. So what we'll have here then is 2 times 5 minus 4y in the quantity. Make sure you put that in quantity, otherwise you'll get wrong answers all the time if you don't distribute things in properly. It's 2 times the whole x, not just the first part of it. And then minus y equals negative 8. And we'll substitute that in. Now, the beauty of the substitution method is now when we move to step 3, we have an equation in one variable. Technically, it's a little messy, but it is in a one variable y that I can solve for. So moving into step 3, we'll have distributing in, we'll get 10 minus 8y minus y equals negative 8. I'm going to root my y, so I'll have minus 8 minus 1 more will be a minus 9. Oops, jumping ahead of my head there. Now subtract 10 from both sides, so we'll get negative 9y equals negative 18 after I subtract 10 from negative 8. And then I will divide both sides by negative 9. So I'll just get y on this side and then negative 18 over negative 9 will equal a positive 2. So I'll get that y equals 2. That's great, but that's only half the battle. Once you get there, substitute the value found in step 3 into one of the original equations to find the value of the other variable. So for step 4, I'm going to just come up here for this. For our step 4, I'm going to plug it into the first one. Why not? Some people may be saying, well, that's this thing over here. Can I use that? Technically, yes, you can, but I'm going to illustrate the steps in their entirety. So y equals 2, I'll have x plus 4 times 2 equals 5. X plus 8 equals 5, which means that x will equal, when I subtract 8 from each side, -3, and our solution is -3, 2. You should always check these. This is one of the places where when I get wrong answers on an exam, it drives me nuts because I know that every single one of these system equations or system problems can be checked when you get to the end. And the only excuse for not getting the right answer on these is because you ran out of time. Always check these. So if I check it in the second equation that I didn't use for getting that solution, -3 for the x, we'll get a 2 times -3 or -6. -2 more minus that y will give me -8. -8 checks out the -8. I like that. So I'm going to say that I did all my math right and move on. So that's with the substitution method. We got our solution -3, 2. Just strengthening some of that terminology. This would be consistent and it would be independent. None of the variables in the solution depend on another. Elimination method. Let's go ahead and see an example of elimination. So with elimination, just going through the steps here, make sure you use all their steps. We're going to choose a variable to eliminate. So first thing I'm going to do is write this system again, and make sure I got that good. So y equals 5. Sure, 2x minus y equals -8. Just double check here because that's number one place where I see people go wrong on these, other than math, is they didn't copy the equation down right. So we got x plus 4y equals 5, and then 2x minus y equals -8. And from here, what we're going to do is choose a variable to eliminate. And when I look at this, either one, the x or the y, nothing's really standing out as being easy. If I'm going to do an easy elimination, what I'm hoping to see is like -2x in one, +2x in the other, and then I add them together, and boom, I'm done. I get rid of the x's. That isn't the case here for the x's and the y. Also, it's not like 4 and -4 or whatever. That would add very easily to 0. So I am going to have to make an adjustment. In elimination method, typically you have to make an adjustment to make variables be eliminated. Well, I'm going to go ahead and pick the y to eliminate for this. And in order to get y to eliminate, so in step 1, we're going to do y, chosen variable, sadly, for y. And then we're going to multiply one or both equations by appropriate non-zero constant so that the sum of the coefficients of one of the variables is 0. Well, I want the variable that I chose, y, to be eliminated. So for the second step in this one, I have to multiply, and back that up there. I have to multiply this equation all the way through by 4. And I'll make that look more like a multiplication symbol there. So multiply the whole equation by 4, and that way I'll have a positive 4y in the one equation, a negative 4y in the other, and they will add to 0. So multiplying the whole equation by 4, we're going to get 8x minus 4y equals -32. That's what we set here. Once you've done that, you add the two equations together to obtain an equation in one variable. So I'm just going to bring down this x plus 4y equals 5 that I got from before, the original equation. All right. Add straight down, I'm going to get 9x plus 0y, which I'm not even going to bother writing, will equal negative 27. Three. Solve the equation in one variable. And this is very nice. We have 9x equals negative 27. Divide by 9, we get x equals negative 27 over 9, which equals negative 3. So now that we have x equals negative 3, which if you remember back to our original approach, works out very nicely for the answer. So we'll have x equals negative 3. Then we'll just take this and plug it into one of the other equations from the original in order to find our y. So I'm going to take that, and for step 5, I'm just going to plug in that negative 3 into the second equation. So I'll have 2 times negative 3 minus y equals negative 8. And we'll have negative 6 minus y equals negative 8. Add 6 to each side, we'll have negative y equals negative 2. Divide by negative 1, multiply by negative 1, negative y equals 2. And your answer is, again, negative 3, 2. I'm not going to bother checking this because we already did that in the first part. But now doing this with elimination, we get the same answer. And that should always happen. If there's an answer, it can be found with either substitution or elimination. Okay. So let's take a look then at some ones that are not consistent and independent as we have here. Some other examples. So let's take a look at number 18. Still going to be solving the system. And they tell you here, they don't care what method you use. So I look at this and I see fractions. Don't freak out. I'm not freaking out. You shouldn't either. I look at it, it's like, ooh, solving, doing substitution. Maybe I don't want to do that. Maybe at this point, looking at an elimination might be nice. If I can multiply one equation by something that will get rid of the variable or a variable in another equation, that'd be the way to go. So what I see here then is a negative 1/2 x and a 3/2 x. And if you see something different with the y's, that's fine, but I'm focusing on the x's here just because that was the first thing that came to my mind. And when I see this negative 1/2 x is positive 3/2 x, if I multiply the first equation by 3, whole equation, if I multiply that by 3, it will give me a negative 3/2 x, which will help me eliminate x when I add the two equations together. And that's what I'm going to run with. So for the elimination, this is the trickiest part, is deciding what to eliminate, and then how do you get the coefficients to be the same numerical value but opposite signs to cancel out, add to 0. So sometimes that takes a little thought, and don't panic if it's not coming right away to you. It takes a little practice. Just got to work on it. So first equation, we're going to negative 3/2 x when I multiply 3 by 3 plus 2y, and then equals a negative 1. And I come down and just go ahead and bring the second equation straight over so that I can add it straight down. And I see 0x plus 0y equals 0, or 0 equals 0. Whoa, what does that mean? Well, as I warned you in the beginning, there are 3 possible cases: one solution, no solutions, or infinite solutions. And when I did this adjustment in that first equation and multiplied through by a 3, I got something that was really close to that second equation. All the terms were the same except their signs were different. If I would have multiplied through by a -3, I would have gotten 3/2 x minus 2y equals +1. I would have got the second equation right back. So when you see 0 equals 0 come out of the elimination method, or even the substitution method, you're going to get something in equality that is a true equality. 0 does equal 0. As soon as you see that, infinite solutions. And when you get infinite solutions, you then are expected to express the ordered pairs in terms of x or y, as in example 4, or we'll just go ahead and do this. So in terms of x, I can always just say, well, x is going to be x. I don't need to do anything different there. But now I need to figure out what y is in terms of x. And for that, I'm going to use the second equation because it's a little nicer with what's already in front of the y. And you solve for y in terms of x. So having -2y equals 1 minus 3/2 x. Divide everything by -2, and we'll get a y equals -1/2 plus 3/4 x. And that would go right here. And they may write it as 3/4 x minus 1/2, just keeping that y equals mx plus b form. But that's all you have to do. In terms of x, well, x is x, and then you solve one of the equations. Doesn't matter which one, because they're technically both the same thing. Solve one of them for y, and you will get y in terms of x, which will fill in the y portion of your point, of your solution. In terms of y, well, you get to put y as y, so that's good. And now looking up above, was there anything nice with it? Now they're both at fractions, so I'm just going to take this second equation again since I'm getting used to it, and we need to solve for x now in terms of y. So I will add 2y to each side, and then I will divide by 3/2 or multiply by 2/3, the reciprocal, on each side. And I'll get a 4/3 y plus 2/3. And then that becomes our x, so I have 4/3 y plus 2/3, and we're done. So they'd be looking for either this answer and or this answer, depending on what their problem set is asking for, in addition to the words infinite solution. Okay. So that's what you'll see with infinite solution. That's why I picked this one. You get a true equality, even though everything cancels out, 0 equals 0, and that indicates infinite. So let's take a look at another one. And again, we are going to solve the system. So for this one, Looking at it, substitution, elimination. Oh boy. I think I'm going to use a substitution because I see this nice singleton y. You picked elimination, tomato, tomato for the most part. Should give you the same answer. So I'm going to pick substitution though here. And we'll get y equals -4 minus 2x. I'm going to plug that into the second equation, or the top equation, more importantly. We'll have 8x plus 4 times -4 minus 2x. This whole expression I found for y, plug in for the y, and then equals 5. And then we'll have 8x minus 16 minus 8x equals 5. And then we'll have -16, because our 8x and -8x will add together to be 0. -16 is supposed to equal 5. That's not true. -16 doesn't equal 5. This is not like the last problem where I got the nice 0 equals 0, or something equals something that was true. Here I'm getting something that is not true. -16 doesn't equal 5, so not a true equality. When you see that, pop out of there. No solution. You're done. All the variables go away, and the things that are supposed to be equal to each other are not. It's not the infinite case, it's the no solution case, and you're done. And that means then that this would be an inconsistent system with independent case. Okay. The last example that I'm going to do for this, it's a kind of word problem. I know some of these word problems get a little crazy, and I want to illustrate at least what you need to be thinking about doing for these. Sometimes different techniques are required, but there are some general things that you should be doing with these word problems in the two variable, two equation world. If I can get this to drag down where I want it to. So we have here that Thursday is ladies' night at the Slurp and Burp Bar and Grill. All beverages are $2.50 for men and $1.50 for women. A total of 956 adult beverages were sold last Thursday night. So if the Slurp and Burp sold a total of 1,996 in adult beverages last Thursday night, how many adult beverages were sold to women? It's like, okay, where do I even start with this? Well, in all of these types of problems, what you want to be looking for, and even though you may not feel that this is a realistic situation, I can tell you that I have used two variable, two equation systems for solving things in real life in a couple of different places at least. I brew beer, and when I'm trying to figure out the water temperature that I need to bring my boil down to so I can mix in water from the tap to bring everything to the proper temperature for fermentation, I use a system of equations. There are other places where this gets used, and it's just a problem-solving technique that you kind of do want to have under your belt, and that's why they make you do it in college algebra. So looking at this, my goal is to try and get two equations out of this so I can use all those techniques I've just been talking about in those other examples. And what I see here is that there's men and women, two different prices for each, and then a total amount of how much was sold when I figure in the amount sold for men and the amount sold for women at those two different prices. I also see, looking at the men and the women, a total amount of beverages that were sold. So if I can relate those pieces of information together in equations, more importantly, two equations, I should be able to use the elimination or substitution method to solve this system. So first thing I'm going to do excuse me, is say that the number of drinks sold to men plus the number of drinks sold to women equal that total of 956. And this is the stuff that you got to be looking for in these problems. You know, one of the key things, even though the names may change, it may not be dollars, maybe percentages, things like that. The things you want to be looking for are, how can I represent the two variables in question in two different equations? And here with men and women, I saw, okay, the number of drinks for men, number of drinks for women, total of 956 drinks. So I'm going to let the variables be M and W, just simple descriptors. M plus W will equal 956. Now I also know that I have a total of $1,996 that was made off of drinks sold to men and women. And if I got dollars here, I better use the dollar information that was also given for men and women separately. So I'm going to take 2.5 or $2.50 times men, or the M, which if I sold 10 drinks to men, I do 10 times $2.50 and see that I spit or got $25 in sales for men. And I'm going to add to that 1.5 times for women. And now in this way, if I know the number of men, the number of women that were in this bar, I can multiply $2.50 by the number of men, $1.50 by the number of women, or I should say the number of drinks ordered by men and women. More importantly, it could be just like 10 people there and they're luscious. But I can take that 2.5 times the number of drinks bought by men, and 1.5 times the number of drinks bought by women, and the dollars made off the men's drinks, dollars made off the women's drinks will be added together to give me 1996. Well, this is a beautiful system. Two equations, two variables. Let's go ahead and solve it. And for this one, I'm going to go ahead and use substitution. So I'm just going to say that the men are equal to 956 minus the women. Plug that in. So I have 2.5 times the quantity, 956 minus the W plus 1.5 W equals 1996. 2.5 times 956. I'm going to go ahead and bring up a little calculator here, because that'll go a lot quicker. I don't want to do a silly math there at this point in the game. And I don't need a big fancy calculator. So 2.5 times 956 equals 2,390. So about 2,390 minus 2.5 W plus 1.5 W equals 1996. Combining my like terms on the left side will give me minus W, minus 2.5 plus 1.5 will be minus 1. I will subtract 2390 from each side. So 1996 minus 2390 will equal negative 394. And means that women will equal 394. And is that what we wanted? Yeah. How many adult beverages were sold to women? 394 drinks were sold to women, which means that the other 500 and something or other, terrible with the subtraction today, but 500 and some change were sold to men. Again, the key in this one, use the information to set up two equations. If they give you dollars as a total and then dollars for each one, multiply those dollars by each variable and set it equal to the total, and then whatever generic total they give you, each of the two variables alone, added together, set it equal to that. And that's that's a typical common approach that you will see with these. Otherwise, again, try to find a way to write two equations relating those two variables from the given information. And once you get those two variables, then you can go into the process of solving the system. Okay, that's going to take us through 11.1. If you have any questions about 10.3 or 11.1 material, as usual, please ask in the discussion area, and I will see you in old cyberspace. Have a great week.